In this question, we are going to find out what are the characteristics of good transconductance amplifier in terms of its input resistance and output resistance, whether they should be low or high, that we are going to find. So generally there are four basic amplifiers. Okay, one is voltage amplifier, current amplifier, transconductance and transresistance. Based on what it accepts as input signal, whether the input is current or voltage, as well as what it is going to produce, whether the output signal is current or voltage. So there are four different cases you will get. Those four, based on those four, these are the four different types of amplifiers: voltage amplifier, current amplifier, transconductance, transresistance. Now we are interested in transconductance amplifier. So transconductance amplifier, as we know, conductance is defined as the ratio of current to voltage. So I by V is the conductance. I by V is the conductance. So output parameter is numerator, input parameter is denominator. So we are making it as I naught Vs. Gain of transconductance amplifier means output by input, I naught by Vs. It is indicated with Gm. So this is a block diagram, and whenever you are applying input signal as Vs and it is producing output I naught is equal to Gm times of Vs. Gm means gain of transconductance amplifier. So, but strictly speaking, we are going to apply Vs. Vs always input source, which will be having some source resistance Rs along with it. Okay, and this I naught, after generating the output, it will be applied to some load RL. When you are applying Vs along with Rs, then this parameter of Vs at input terminals, okay, will be treated as Vi. It is not Vs, it will be treated as Vi, because effective input signal after taking a drop across Rs and voltage across RL is V naught. It is totally depending on the how much current it is going to give as output, I naught. Okay, so we will see what will be the value of Ri and R naught. That means you must replace the block what we have indicated with transconductance amplifier with its equivalent circuit. Okay. So always any equivalent circuit will be having a simple input resistance at the input part, and output is totally depending on the type of output signal it produces. If it is producing output signal as current, there must be a Norton equivalent. If it is producing output signal as voltage, there must be Thevenin's equivalent. So this is Norton equivalent of current source. At the output side, input side always Ri is the input resistance. So voltage across Ri is treated as Vi, and current coming out of this R naught is I naught, and actual current source what you are going to get is Gm times of Vs, Vi. Effective input signal multiplied by gain of this transconductance amplifier, that is Gm. Okay, so add load resistance as well as source resistance with Vs. This is Rs and it is RL. Now we are going to find out, our ultimate aim is to get I naught is equal to Gm times of Vs. But you will not get I naught is equal to Gm times of Vs, because some part of Vs is dropping across. Because some part of Vs is dropping across Rs, then the remaining is only available as effective input signal Vi. That Vi is multiplied by gain Gm times, and out of that one, this current is also gets divided into R naught as well as RL. So with some restrictions, you can get I naught is equal to Gm into Vs. What are the restrictions? That we are going to find, which gives the characteristics of transconductance amplifier. Now I naught is equal to, first step, I naught is equal to Gm times, I naught is equal to, if you want to get I naught is equal to Gm times of Vi, what must be the relation between R naught and RL? So when R naught is equal to very small, when R naught is very large than RL, then maximum current is going through lower resistance. According to current division rule, more current flows in lower resistance. Okay, so RL must be, if you want to get RL should take maximum current, that means R naught should be very high. So if R naught is very high, then the load resistance can be anything. Depending on the load, the RL may varies, but if you choose the transconductance amplifier whose R naught is very high, that means irrespective of RL, always the generated current is going into the load. That means you can say it as R naught is equal to infinity ideally. Ideal value of R naught is infinity. Next, so if Vi should be equal to Vs, then okay, and if Vi has to be equal to Vs, okay, then you can write it as I naught is equal to Gm times of Vs, which is our required one. But what condition this is going to be happening? This happens when Ri is very large compared to Rs. If input resistance is very large, then maximum voltage applied is drop across that Ri. Irrespective of Rs, if Ri is very large, then you will get effective input signal as applied input signal Vs. That means Ri should be equal to infinity. This is ideal value. Ideal value of Ri is equal to infinity. Ideal value of R naught is equal to infinity. So then it is going to act as good transconductance amplifier. So if you use these two values, how the circuit is going to be, internal block diagram of transconductance amplifier will be looks like. It will be looks like in this way. R naught is very large, so it is acting as open circuit, and Ri is also very large, that means open circuit. So if you are going to get open circuit, this is actually what you are going to get within. So if you connect any source with Vs, if you connect any load with RL, okay, definitely I naught will be equal to, first Vi is equal to Vs, because current flowing through this one is going to be 0. So whenever current is 0, there will be no voltage drop across Rs. So Vi is equal to Vs, and this effective input signal is multiplied by gain times. So you will get it as Gm times of Vi, that means Vs, and as there is no output resistance, I naught will be equal to Gm times of Vi, that means Gm times of Vs. So applied input signal voltage is multiplied by the gain times of transconductance amplifier. This is the good transconductance amplifier. So the right answer for this one is both are very high. High input and output resistances. So the right option for this one is C. C is the right answer.